Hello, this is Gene Fry. I've been studying climate change for 31 years. I'd like to share with you what I've learned through my own research and building on the research of many other people. So let me share my screen with you and get to my presentation. Albedo changes are key to understanding our past and especially our future. We can learn lessons from the distant past. The red area tens of millions of years ago is much warmer than now. See the temperature spikes in the past, like those in the one in the present we're going through. With more ice and snow, albedo changes are much larger. The thermometer era record land has warmed much faster than sea surface. Combined 1.2 degrees Celsius in the last century. Especially fast in the last decade. Not too long before we get to 2 degrees. Las Vegas is really very hot, especially June through September. When do these states become as hot as Las Vegas? You'll see numbers for each state. Dates, years. Assume trends over the last 21 years continue. Arizona, Texas, Idaho, South Carolina, Kansas, Oklahoma, Georgia, Alabama, Colorado, Utah, Louisiana, North Carolina, Wyoming, Tennessee, Mississippi, Virginia, New Mexico. Speed this up a bit. California, 2194. New England, where we're having the conference. The water states and the far north. Look more at the acceleration in the next two slides. Only some 1% of the heat gain goes into the air, which is what we care most about. Above the purple at the bottom is melting ice in gray. Land going down many meters in light brown. The deep, deep ocean below 2000 in dark blue. The medium deep ocean in medium blue, and the upper ocean areas in lighter blue. Almost all 90% of the heat goes into the oceans. Here we can look at the acceleration I mentioned. One of those tick marks is 100 years of US energy use. So for the first 23 years, we're looking at 40 years of US energy use going into the ocean each year. 70 and 100 years each year. The acceleration. This is more than all the energy humans have ever used by about tenfold. Keeling curve, I think you've seen before. This is without the sawtooth because it's annual averages. Methane is up more steeply, especially in the 19th century. That's the maximum between ice ages. Today, CO2 level is the highest since 14 million years ago. Things were much hotter then, and seas were much higher. Almost as high 4 million years ago. Much warmer than now and not quite as hot. Higher seas, a lot. The water to raise sea levels came from Greenland and Antarctica, including some of East Antarctica. That's been documented for past ice ages. Big lag effects. One of the ice cores from Vostok near the North Pole, South Pole. Temperature, methane in the middle, carbon dioxide on top. Both of those are currently off this scale. The next slide, we'll get rid of the time axis and plot temperature on the bottom against CO2 at the top. Sampled every 10,000 years is blue dots. The purple dashed line is the trend line, the best fit by linear regression using just the CO2 information shown there. When you add the methane from the middle graph on the preceding page, you get the green trend line. Here's its equation. Explains more of the variation. Now convert Antarctic temperatures to global temperatures. I use Snyder's work. There's what I get. The relationship 4 million years ago and 14. I was surprised to find such a good fit to an era colder than now. Current levels of CO2 and methane. 8.5 degrees Celsius warming based on Vostok ice core. I'll change that a bit near the end of this slideshow. There's a green equation again for the trend line we saw in the previous slide. Plug the numbers in, and to hold warming to 2 degrees requires 314 parts per million in pre-industrial CH4 levels. We need to remove 3/4 of the CO2 we've emitted and any future emissions. Our remaining carbon budget is not 800 billion tons we can still burn, but negative 325 we have to take out of the air and not put any in. Albedo effects are key. 5 major categories: clouds, sulfates, sea ice, snow, and land ice. We'll visit each in turn. The other major feedback is water vapor. Very important. Clouds, this is the best graph I've found. Low amount is less area. High altitude clouds increase while low altitude ones decrease. Clouds get thicker and darker, so that's a cooling effect, but the others outweigh it. 0.47 here is less than what the IPC uses, came to as a central estimate, but it's what I use in my model. Sulfates. Volcanic eruptions stand out. I did the regression zeroing out the volcano years. So I just looked at 70 years of data rather than 120. Human sulfur emissions went up a lot, and that cooled things off. Another major volcano. Europe and the US cleaned up their sulfur emissions. That raised temperatures a lot. Our emissions of sulfur are down almost a quarter from their peak, but they're still 3 times what they were at the beginning of the thermometer era. There's the equation, best fit, very high R squared, very high T ratio, significant 99.9%. From the lowest temperature to the highest on land, 1.8 degrees Celsius. Arctic Ocean ice is shrinking fast. A few details here. Area and volume is a steeper decrease because the ice got thinner too. 3 dimensions, not just 2. Earth absorbs more heat, positive or amplifying feedback. Even if we don't put more CO2 in the air, there's a lot more warming will take place. Looking at volume tells a better story than just the area of how long the ice will last. The minimum ice month, we may be looking at some ice-free this decade and ice-free by fall around 2040 something and gone all year around 2080 based on those extrapolations. So how does that affect overall global climate? If you lost all the Arctic ice, calculations 0.7 watts per square meter. It's about a third, something like a third as much as CO2 that we've emitted. And Arctic ice hasn't clearly begun receding yet. Snow, 2 looks. First at timing. That added 12% to greenhouse gas warming, about half as much as Arctic sea ice, or a quarter as much as all sea ice. Now, based on the area, which will decrease as Earth warms up, snow will stay on the ground, arrive earlier, leave later. There will not be as many days with snow on the ground. So I looked at a bunch of US and Canadian cities with various adjustments, get 9 degrees shrinkage of snow per 1 degree of global surface warming. Contact me for details on that. Land ice around both poles. Greenland, Antarctica. In both cases, the acceleration is 12% a year. The velocity of ice loss will keep increasing even as acceleration doesn't accelerate as much. But land ice area decreases far more slowly than sea ice area. So the albedo change is very little so far. Water vapor is the key greenhouse gas. Warm the air, it contains more water vapor. That boosts what we often call the effect of CO2, methane, and other greenhouse gases. Going back to 1975 and forward to 2400. So putting back together sulfates, snow cover, sea ice, land ice on the horizontal lines. The middle column also looks at the feedbacks from cloud and water vapor. 0.33 is the total effect. Sulfates are the most important, followed by snow cover, then Arctic sea ice loss. Direct changes and the indirect. 39% of observed warming is due to albedo changes and their feedbacks. Let's break that down a little bit. As I mentioned, a lot of what's often assigned to CO2 is actually water vapor. It's true also for methane and other greenhouse gases. So I'm assigning them to water vapor. Water vapor, CO2, sulfates, cloud changes, and methane are the chief players. Also substantial, snowmelt. This is looking backward, by the way. other greenhouse gases, sea ice, and land ice. Albedo changes for the last 40 some years are comparable in their warming effect with our own greenhouse gas emissions. Albedo changes will become dominant as the future unfolds. 3 to 4 times more, even if CO2 levels don't change if we quit cold turkey. Sulfur, sea ice, north and south, snow, land ice, oceans giving back some of the heat they've absorbed, water vapor and clouds. If we wait 15 years to peak emissions, things get a lot worse. That's just over 5 degrees Celsius more warming, in addition to the almost 4 we have contracted for already. Permafrost contains more than twice as much carbon as the atmosphere. The lower right is and reflects best the temperature profile we'll be coming up with, and also climate sensitivity, which I'll cover near the end. So we're looking at somewhere from 0.3 to 1.2, 1.5 degrees Celsius warming from permafrost. Probably a little closer to the bottom of that. I'll deal with that a bit later on. So time perspective. So I developed 6 scenarios from top to bottom, the key on the left. Peak year for our emissions. Orange is when we phase out fossil fuel by 2050. We've already peaked. Cold turkey is when we quit emitting fossil fuels immediately and forever, or for the rest of human civilization. Eliminating fossil fuels and removing CO2, carbon dioxide removal, CDR, in blue and green. So we've lost a lot of carbon from soil by plowing it and other things. Blue is replacing about half that, and green is replacing basically all of that. Here's how it translates to CO2, not just our own emission, but the feedbacks we've unleashed from permafrost, etc. A large fraction of that is from permafrost, etc., which includes warming soils, warmer ocean, methane hydrates, and forest fires. So there's our emissions, 700 plus 450 from permafrost, etc. 2015 peak 600 plus 340 is 940. Eliminating fossil fuels by 2050, 500 of our own, 220 from permafrost, etc. The others are in better shape. Looking out over the rest of this century, the results are not terribly different from other models. You will see the cold turkey case. We stop burning coal with its sulfur immediately, or at least stop putting sulfur in the atmosphere immediately. That raises temperatures several tenths of a degree immediately, but we're better in the out years. Now looking out to 2400, putting it all together. There's our 2100, where the previous slide looked out to. The Paris target. In brown is the highest level that the Stern review from British government in 2006 considered. That's a level where civilization collapses because most of all, lack of food. 10 degrees is borderline extinction. There'll probably be a few humans still around. So these are the factors, then the projected warming. Human emissions are on the third line. They're the third most important numerically. These scenarios go from left to right, 2035 peak to carbon dioxide removal ×2, phase out fossil fuels. The lines, the top one has the highest average across the 6 scenarios, 1.61 to 0.49 at the right. And the second most important is loss of snow cover. Our own emissions are third most important. They're the highest for the factor for continuing to burn fossil fuels, but they're negative actually when we remove CO2. Cloud covers next. Our own sulfur emissions phased out in all cases. Arctic sea ice is gone in all cases. Antarctic sea ice is cut back, but may some of it, if we stop burning soon, will remain. Permafrost emissions, the other natural reservoirs, soil, ocean biomass, methane hydrates are set at half as much. Warming the deep ocean, land ice shrinkage doesn't convert to very much warming. And at the bottom, you see the temperature rise above today's 1.6, I think, actually, for the land surface, 1.1 for combined land and sea. Look now at climate sensitivity, which I think has been underestimated very consistently. So here we have our graphs for CO2 and temperature. Long-run climate sensitivity is the eventual warming from doubling CO2 in the air, but it is not constant. It decreases as ice and snow area shrinks. Looking at the Vostok ice cores, when we had a lot of ice and snow mostly, you get a high number, about 8 degrees Celsius for climate sensitivity. But 2/3 of the ice and snow have vanished in the last 25,000 years. So for us, it's going to be less than 8. Now to estimate that, look at the figures at the left, cold turkey magenta, fossil fuel elimination in orange. Halfway between is 560. In the lower figure, halfway between is 6 degrees. The estimated climate sensitivity is 6 degrees, looking forward from 1880 to late this century. 2035 peak scenario, sensitivity is almost 4 degrees instead of 6 or 8. Now, what we need to do, as we all know, we need to stop putting carbon in the air. As many of us know, we also need to take it out in very large amounts. Fortunately, stop putting carbon in the air is the cheapest way to go. Solar and wind power are now cheaper than any other form of energy. They're cheaper than natural gas combined cycle across most of the US, cheaper than continuing to operate coal-fired power plants, and that's probably true in most of the rest of the world. So we have been getting more from solar and wind. In the US, the renewable energy has increased, doubled in the last 10 years from 10 to 20%. Coal share as a very expensive source has plummeted. A little bit of that's due to COVID, but mostly it's structural. Transportation is now the biggest source of carbon emissions in the US as we're getting a greener grid. That will change. Electric vehicles will replace petroleum ones as they become cheaper. Their variable costs are already significantly lower. The primary variable cost is replacing the tires every 60,000 miles. As a result, oil use will fall steeply. Oil companies will go bankrupt and reconstitute themselves, still sell oil. US CO2 emissions were down 15% by 2019. They're down more steeply thanks to COVID. They'll bounce back, but not all the way to peak. What we need to do, the best policy is tax carbon worldwide upstream. Start low, rise substantially and briskly on a preset trajectory so people can make their plans in their spreadsheets to do their investments. Individuals and businesses. End subsidies for fossil fuels. My proposal, give carbon tax credits for carbon removal from ambient air at the same rate carbon emissions are taxed. There's one of my favorite trajectories. There are others that are also reasonable. The proceeds from the tax should be returned as monthly dividends to individuals. Poorer people who use less energy will make out well. They'll get more money back than they spend for higher fossil fuel prices. Rich people can afford to use less. And this is very beneficial to the economy. So what we need to do, the biggest industry on Earth, the second half of this century, and perhaps the biggest by mid-century, is taking carbon out of the air. Gold standard is direct air capture. It takes an awful lot of energy to do that. Don't do it too much. Well, you don't have a green grid, but you can pipe the CO2 underground. It turns into rock within 2 years. Organic farming is the big one right now. It's fairly cheap. The problem is it will come out of soils as the soils warm up farther. Same problem with forests. Farming the oceans may or may not do much. Mangrove forests are wonderful. Coral reefs will be gone. Biochar is great stuff. It's very human labor intensive. May be able to do something with short rotation cattle grazing if you get the methane emissions under control. Problem with forests is that forest fires accelerate 7-fold for each 1 degree Celsius warming. So in summary, we must go carbon negative big time by 2050. There's how to get in touch with me and my website. So I'm going to stop sharing so that I can stop the